my name is Sergio Dorado-Rojas, a second-year PhD student at RPI, and this work, titled Time Domain Simulation Performance Benchmark between Modelica and Dymola, was developed with my fellow PhD students Manuel Navarro Catalan and Marcelo Castro Fernandez, and supervised by Dr. Luigi Panfretti, head of the LSAT lab. This presentation is structured as follows. First, I will describe a little bit of the motivation behind this work. Then we will dive into the details of the implementation of the test system using the OpenIPS library. The test system is the EEE14 bus grid. And afterwards, I will make special emphasis into the experiment setup, describing the automation procedure, and showing some important simulation results. Lastly, we will see the most important performance metrics, and we will discuss the performance scores, and finally we will conclude this presentation by illustrating a few ideas of our future work in this direction. So a little bit of background. Computer-based simulations are a common practice in power system studies due to the inherent interconnected construction of electrical grids. Moreover, due to the increasing penetration of renewable energies, the complexity of the individual device models has increased, thus bringing up the requirements on computational resources to perform simulation-intensive analysis. And in this context, Modelica represents an accurate, equation-based, multi-domain environment to perform power system simulations with the state-of-the-art tools. And this tendency, however, is not exclusive to power systems, since during recent years we have seen how many disciplines have started to incorporate Modelica in their workflows, which has led to the development of many open or some proprietary libraries. But we have to ask ourselves, how does a user that just transitioned to Modelica learn to use the tool? So most commonly, this person will bounce to an open source alternative such as OpenModelica. However, more specialized users will rely on commercial tools such as Dymola that provide advanced functionality satisfying industry-specific requirements. So at this point, it is normal to ask us, how do open source tools measure up to software with a price tag built to operate on the same language? So this work addresses this question by performing a comparison using a power system benchmark between OpenModelica and Dymola for several solver settings. So a little bit of the methodology of this work. So the proposed benchmark was developed following the next steps. First, we have modified the EEE14 bus system containing the OpenIPS library to have 3 different simulation scenarios. Then we have automated the execution and the performance score computation of the different scenarios for each tool using the corresponding Python APIs. And lastly, we have gathered some metrics describing the performance of the tools for each simulation with different solvers. So before going into the implementation of the details of the code, we would like to mention something about the OpenIPS library. So this is an open source Modelica module that contains a set of components to perform phasor domain modeling and simulation. Most of the models in the library have been validated against commercial tools, mostly PSSE, which is an industry de facto standard in North America. And some of the advantages of using this tool are derived from the Modelica language itself, like unambiguous model exchange and mathematical description of models. But another worth highlighting are the separation of models from tools and solvers. That means that the model is not adjusted to the analysis being performed, which is the normal practice in power system software, and the use of object-oriented paradigms which simplify automation. So you can check the library by clicking on this link afterwards. So here on the left, we see the implementation, the single line diagram of the 14 bus system, and on the right you can detail the OpenIPS presentation. And we must underline that we introduced some components to produce discrete events. In this case, this is a bus to ground fault. So the testing scenarios, as we mentioned before, we will evaluate the simulation for 2 different Modelica software tools. One is Dymola and the other one is OpenModelica. For the solvers, from those the 2 tools have in common, we have selected a variable step solver such as Dazzle, and 2 fixed step solvers such as Euler and the trapezoidal method or Runge-Kutta. As for the different scenarios, we have three different configurations. One is the model initialization. Here, basically, we have provided the model with an ill-conditioned power flow solution. In other words, the model has to compute, has to integrate the initial conditions because the initial conditions do not correspond to the dynamic equilibrium. Then we changed and we open a line. So this can be classified as a smooth fault because the dynamics that are produced by this are not that do not excite that many modes of the model. And the last one is R2 bus three-phase to ground faults, which are more severe faults that will excite and will trigger more dynamics in the system. So how the simulation was automated. So first of all, I would like to say some details about the configuration of the equipment that we have used to execute the code. So basically, you see that this was an Ubuntu machine with 12 cores. Each of these supports 2 threads. And the releases that we have installed were Dymola 2020X and OpenModelica 1.14.0. So then here on this diagram, you can detail basically how the simulations were automated. We mentioned before that we have done it through Python because it was easier to change the settings and automate everything. So at the beginning, the scripts are pretty similar. So basically, at the beginning, we open the model and we open the library, the OpenIPS library, and then the model. Then we perform initialization. We change the simulation settings, and we set the solver settings depending on the scenario that we would like to analyze. And then after the integration is completed, we take the results, perform some automatic analysis, like the ones we will show afterwards. And we will get here some numbers based on which we quantify performance with some simple metrics. So here, basically, one of the reasons why we used Python was to take advantage of the robust and the really well-documented APIs of each tool. And performance has been measured using a parallel process. So basically, we have forced the tools to use only one core for the simulation. And in a parallel process, we have executed the script to measure the performance of the tools. You are encouraged to check the full code in GitHub here below. So some simulation results. So what we have done here was to guarantee that we were getting exactly the same or really close results with both tools. So here we plotted on the same graph some signals, in this case voltages at a given bus for Dymola and OpenModelica, and then we computed the normalized absolute error. So we can see here that the results are in the order of 10 to the minus 6 or 10 to the minus 8. So basically, they are identical. One thing that is worth mentioning is that this spike here is due to that ill-conditioned power flow solution that we fed the model with at the beginning. But that was done on purpose, so that won't be the case in a normal simulation study. So some results here. You can see more numbers in the paper, but here we have summarized the execution time for both tools. So we can conclude really, real quickly from here that Dymola performs way better than OpenModelica for the variable step solver. And this is due to the developments that the Dassault system people have done in the software in recent years. But however, we see that OpenModelica performs better, not with that much of a difference as in the variable step case, but performs better than Dymola for fixed step solvers. So to see this more clearly, we have proposed a metric known as normalized minimum execution time. So this is basically the minimum execution time for a given scenario, a given solver as well, for a given scenario for the solvers that have been for the solvers that have been used divided by the estimation the execution time of each tool. So this metric here will be maximum when the execution time of the tool is minimum. So here we see that Dymola performs way better than OpenModelica. So we can compute the ratio of 1 to each of those, and we will see that it's about 50 to 11 times faster. But for the fixed step tools, we see that OpenModelica performs better, but the difference is not as huge, not as so that the margin is narrower, but still significant, but narrower than in the fixed than in the variable step case. So we have consulted Dassault about this, and they have said that thanks to these performance errors, they have discovered some bugs in the GCC compilers, and they will fix that for future releases of Dymola. So yeah, I have already talked about this. So some future work, basically what we want to do is to scale up the experiments and to work with a larger power system. We want to focus on the Nordic 44 model, that is the largest one that is available in the OpenIPS library. And then we want to study the effect of different features of the tools, such as the AE solvers and sparse solvers with Dymola and OpenModelica. Of course, we would like to evaluate how the tools have been improved with the latest releases. By the time of this presentation, the latest Dymola release was Dymola 2021 and OpenModelica 1.14.0. Sorry for the typo here. And of course, we'd like to test the benchmark in different computers to see how the resources are used for by the tools in each and in different environments. So that was everything for this presentation. I would like to thank you for your attention, and I look forward to answering your questions in the Q&A. Thanks. Bye-bye.